1915, two South Australian research scientists, William Bragg and his son Lawrence Bragg, shared the Nobel Prize for their analysis of crystal structure by means of X-rays. Their device and the machines which followed would revolutionise chemistry. Little remembered here by a country that chooses to turn its back on science, they were showered with honours and headed the most prestigious laboratories in Britain. This X-ray spectrometer was their invention. It bombards materials with X-rays, producing a diffraction pattern, like interfering ripples in a pond. A modern X-ray crystallographer can produce a three-dimensional picture showing the densities of electrons within a crystal. That allows us accurately to measure the sizes and positions of atoms and the lengths and types of chemical bonds between them. We can image metals, metal alloys, ionic and covalent crystals, rocks, and even the chemicals of life. This diffraction pattern from the Mars rover in 2012 has allowed us to identify pyroxene, felspar and olivine minerals in the Martian rocks. Young Lawrence Bragg headed the Cavendish lab where Watson and Crick and others used X-ray diffraction patterns to identify that DNA had a double helix structure. Modern Australian researchers continue to push the boundaries using the 3 giga-electron volt Australian synchrotron near Monash University in Melbourne. Instead of X-rays, it fires electrons at targets near light speed. They model the structure of the most complex molecules of nature. The overwhelming majority of the 92 natural elements are metals. Those that are not include hydrogen, plus a small number of elements clustered at the top right of the periodic table. Those in yellow are non-metals, and in green, semi-metals. The rest of the table should be coloured blue for metals. Metals are those whose outer valence electrons are easily lost. They dominate the left of the table because those elements prefer to lose their few outer electrons to leave a full outer shell. Metallic properties increase down groups, as in fatter atoms the outer electrons are less tightly held by the positive nucleus. Transition metals in the centre of the table have overlapping outer shells, allowing freer movement of outer electrons. The situation is complicated when we consider their electrons as wave shapes that can overlap. All metals have a number of free electrons wandering through the crystal lattice randomly and at high speeds. The metallic bond is an attraction between the big metal ions and the sea of tiny wandering electrons. The bond varies dramatically in strength. Sodium melts easily and can be cut with a knife. Tungsten melts at 3,422 degrees Celsius and is quite hard. Metals can be alloyed by adding other metals or silicon or carbon. This changes melting point, hardness, malleability and resistance to corrosion. The skills of alloying metals are hard won and are being lost by our nation as industries close. This diagram shows why metals are malleable and ductile. If you push this row of ions along, there is little change to the crystal structure, so it can be pounded easily into new shapes or drawn out into wire. Historically, the Metal Age replaced the Stone Age. Metals conduct heat. The free electrons simply vibrate faster in their random movements. The acceleration effect is quite rapid, so metals heat up faster. Metals conduct electricity. Apply a voltage across a wire and the dancing mass of free electrons will drift slowly towards the positive plate. These copper cables contain drifting free electrons pushed by tens of thousands of volts at the local power station. The first crystal to be solved using X-ray diffraction was sodium chloride. The Braggs realised that electrons had been transferred from the sodium atoms to the chlorines. It forms an ionic crystal held together by strong ionic bonds between the sodium cations and the chlorine anions. Each ion is surrounded by 6 of its opposite partners. The ionic bond is a simple attraction between opposite charges. The first attractors in ionic compounds are the metal ions or ammonium radicals, which come first in compound formulas. They bond with a limited number of non-metal anions from group 7 or possibly group 6 in the periodic table. These are written second in the formulas using IDE names. Instead of non-metals, a wide selection of negative radicals are available. In water, the ionic bond is often broken and the crystals dissolve. The lone pairs of electrons in the oxygens surround the metal cations and break up the crystal marriage. In group 4 of the periodic table, we find the elements carbon and silicon. Carbon is responsible for the complex molecules of life, and silicon dominates the rocks that make up most of the Earth. They both have half-complete valence shells and are electron sharers. They form covalent bonds in their search for full outer shells. Their element allotropes form covalent lattice structures. This is the high-pressure allotrope diamond that forms in deep volcanic kimberlite pipes. These carbon tetrahedra are repeated billions of times to make a single hard diamond molecule. The silicon crystals that we grow in furnaces have a similar structure. Another allotrope of carbon is graphite. It flakes into sheets. Each sheet is a giant molecule. The bonds between the sheets are very weak and will conduct electricity. We use graphite in pencils, as a dry lubricant in locks, and as electrical contacts in spinning motors. The mineral quartz sand is silicon dioxide. The silica tetrahedra that it forms have the same structure as diamond. So quartz is harder than steel. Carbon partners with hydrogen, a range of nonmetals, and a few metals to form the big molecules of life called macromolecules. Meddling humans have created many compounds of carbon not found in nature. Some of these are life-saving chemicals and some are evil. Molecular chemicals are usually defined as having 2 or more atoms bonded together into small molecules by covalent bonds of shared electron pairs. Elements which prefer to share electrons include carbon, hydrogen, and the nonmetals on the top right of the periodic table. This table shows prominent molecular elements. All are held together by covalent bonds of 2 shared electrons per single bond. Most have electron lone pairs, making them reactive to other chemicals. Yet all have low melting points. The bonds between these molecules are weak. Nitrogen and oxygen make up the most of our atmosphere. Hydrogen is made by electrolysis of water. The group 7 halogens are dangerous and should not be breathed in. We make them by electrolysis of their salts that are found in seawater and seaweeds. Here is a selection of natural molecular compounds. They contain 2 different elements. Each has a shape defined by the repulsion between both bonds and lone pairs. Water is the only liquid at room temperature. Its intermolecular bonds are a bit stronger than the others and are called hydrogen bonds. Water dominates the second outer layer of the planet, the hydrosphere. The others are all gases which play a role in the atmosphere. This space photo shows just how thin our atmosphere is. The orange layer is the troposphere, containing 75% of the air and averaging just 12 kilometres thick. Here is my brother-in-law, Dr. Ian, having trouble breathing at Everest Base Camp, altitude 5.6 kilometres. Here are some of the chemicals that we have seriously unbalanced in the Earth's great natural cycles. Our survival depends on the ability of the Earth's leaders to reverse the damage. I invite you to research ways to help them achieve the honourable goal.